Yeah, okay, great. So thank you for having me. I'm going to be talking about a marking graph for finite-type Artin groups. So we're just going to start with a little bit of an introduction to what the terms in the title are. So first, we need to define a marking graph. A marking graph was originally defined for mapping class groups. So if you've not seen a mapping class group, the mapping class group of a surface is the group of orientation-preserving homeomorphisms of a surface which pointwise fix the boundary, considered up to isotopy. And any punctures on the surface can be permuted. So for today, we actually only care about one mapping class group. And specifically, we care about the mapping class group of the n-punctured disk. So that one has a special name. That's called the Braid group. And to see where the name comes from, you can kind of imagine some strings coming up from the punctures on the disk. And as I do elements of the mapping class group, which move the punctures around on the disk, that's going to create some twists in those strands, which are called braids. Okay, so that's the mapping class group. The mapping class group has, for a very long time, been studied by its action on what's called the curve complex. So the curve complex of a surface is a simplicial complex where my vertices are going to be isotopy classes of essential simple closed curves. So by essential, I just mean not homotopic to a point, a puncture, or a boundary component. And you can see some examples of essential curves in these blue curves down here. And I'm going to put edges between any curves that are disjoint. Okay, and then I'm going to fill in any simplices where I see pairwise connected vertices. So that's the curve complex. And mostly we're going to care about maximal simplices in the curve complex today. So what do maximal simplices look like? Maximal simplices are collections of curves which cut the surface into pairs of pants. So I've drawn one here. This is a genus 2 surface. And if I cut along each of these three curves, alpha 1 through alpha 3, you can see that, okay, I cut my surface in two. And if I were to pull apart along alpha 1, I would pull that out and it would sort of look like the legs of a pair of pants. So that's where the name comes from. So that's what maximal simplices look like. The curve complex is hyperbolic, it's infinite diameter, and most importantly for us today, it's finite dimensional. So what that means is there's always a finite number of curves that give me a Pants decomposition of the surface. My maximal simplices are finite dimensional. Okay, there's a very natural action of the mapping class group on this curve complex. It sends the curves to their image under an element of the group. And the mapping class group of a pair of pants is trivial. So our Pants decomposition is cutting our surface up into pieces, each of which individually has trivial mapping class group. And so a natural question you could ask is, if I know where an element of the mapping class group sends a maximal simplex, is that enough for me to reconstruct the element of the mapping class group, since those curves are cutting the surface up into pieces which each had trivial mapping class group of their own? The answer is no. So Pants decompositions have stabilizers. And these stabilizers are generated by Dane twists around each of the base curves, so the curves in the Pants decomposition. And the important part of a Dane twist for us today is that this is some element of the mapping class group which is supported on an annulus based around a single curve. So there's a Dane twist, which is an element of the mapping class group, which does something non-trivial on an annulus around alpha 1, for example, and is trivial on the rest of the surface. Okay, so these are infinite order elements, is another important property of Dane twists. So these Pants decompositions have infinite stabilizers. But you could ask, maybe there are some more curves that I can add into this, which would keep track of those twists that are stabilizing Pants decompositions. And if I added in some more stuff to keep track of those stabilizers, then would I be able to say yes to my question? Would I be able to reconstruct an element of the mapping class group by looking at how it acts on some finite collection of curves? Okay, so spoiler, the answer is yes. And a marking gives you exactly the curves that you need to add in to keep track of the stabilizers. So this was first defined by Masur and Minsky in, they had two papers in 99 and 2000. So a marking is going to be a set of ordered pairs of curves, alpha I and ti are both curves, which satisfies the following conditions. So first of all, the alpha I are going to be Pants decomposition. So I'm starting with the Pants decomposition of my surface. And the ti are going to be some set of curves that keep track of those Dane twist stabilizers. So specifically, I want alpha I and tj to be disjoint when I is not equal to j. And so that means that the curve tj is not in the support of the Dane twist around alpha I. So the Dane twist around alpha I shouldn't change tj. And then when I look at alpha I and ti, so the same index, I want them to have the minimal possible non-zero intersection number. That's a technical condition to control the number of markings with a particular Pants decomposition base. So that's the goal of that condition. Masur and Minsky also defined two different moves between markings. So there's a twist move, which takes one of these tracker curves Ti and replaces it with its image under a Dane twist about the corresponding Pants decomposition curve. So it says this Ti's job is to keep track of Dane twists. I'm going to do a Dane twist and replace it with its image. A flip move does something slightly more complicated. So in essence, a flip move interchanges the roles of alpha I and Ti in one of these pairs in my marking. And then I have to adjust some of the other curves appropriately, and I'm going to show you what I mean by that in the next slide. Okay, so here's an example of a marking, which is a little bit small because my computer's not cooperating, so apologies for that. But I have these blue curves that I had before, so this is the same Pants decomposition. And I've added in some collection of curves T1 through T3. So 1, 2, 3 goes left to right. So at the beginning, I start with a marking. In the middle, I've interchanged the role of alpha 1 and T1. So they're in opposite colors now. But this doesn't actually give me a marking because I had no conditions previously on how these tracking curves were allowed to intersect each other. And so if I just interchange the roles of alpha 1 and T1, T2 winds up intersecting something that it shouldn't. And so I have to make some modification to actually get a marking out of what out of this flip. But Masur and Minsky proved that you can always do that. So there's always some appropriate replacement curve you can do. And they were then able to define the marking graph. So the marking graph is a graph where a vertex is a marking, and two markings are connected by an edge if they're connected by one of these elementary moves, so either a twist or a flip. And they proved that the action of the mapping class group on this marking graph is geometric. And so importantly, that means that there's a yes to our question, and vertex stabilizers are finite. Okay, and I'm not going to say too much about this third point, but the existence of a graph like this, the existence of the marking graph for mapping class groups and similar kinds of graphs for other groups, is one important component in Masur and Minsky's hierarchy machinery for mapping class groups, which was later generalized to hierarchical hyperbolicity for other groups. So that's kind of some motivation for looking at marking graph-like objects. Okay, so this is a good place to pause for questions, I think. Any questions about mapping class groups or the marking graph? Good, okay, great. So that's part one of the title. Part two of the title is finite-type Artin groups. So we talked about braid groups. They're mapping class groups of punctured disks. Finite-type Artin groups generalize braid groups. And so in particular, they're groups with similar types of presentations. So the braid group is generated by elements which take string I and twist it over string I plus 1. Those collection of elements generate the braid group. And if I wanted to ask what relations I need in a presentation that uses that generating set, okay, well, first, maybe things that use strings 1 and 2 should commute with things that only use strings 3 and 4. So that's fine. And then I would also need the braid relation, which is pictured here. And that says that crossing string 1 over string 2, and then 2 over 3, and then 1 over 2 again. You can imagine picking this top string up and pushing the crossing underneath it with your finger to get from the first picture to the second picture. And the second picture crosses 2 over 3, 1 over 2, and then 2 over 3. Okay, turns out those are the only relations you need to define the braid group with that particular generating set. And so an Artin group in general is a group which admits a presentation of a similar form. So there's some finite generating set, and all of the relations look like alternating products of two of these generators. Okay, there are many ways to define a finite-type Artin group. For us today, it's going to be a group where the relations give you a graph of one of the following forms. And so the graph is just telling you how to encode the relationships between different generators. So each of those generators should give you a vertex in the graph, and then the label that connects them in the presentation is encoded in the graph. So these are the finite-type defining graphs. Yeah, good. No label is a 3 and no edge is a 2. Okay, questions about Artin groups? Great. Okay, a little bit more background about Artin groups. The subgroup of an Artin group generated by a subset of the Artin generating set, so the generating set in that presentation, is called a standard parabolic subgroup. And a conjugate of it is called a parabolic subgroup. The element G is called a standardizer. So that's just a representative for the parabolic subgroup. And it's called irreducible if the subset of the defining graph that I picked was connected. So in particular, if the subgroup doesn't decompose as a direct product. Okay, the key point for us is that in the Braid group on n strands, parabolic subgroups are in bijection with curves on the n-punctured disk. And so you can kind of visualize that projection as follows. If I start with this picture on the left, where I have a green curve enclosing 3 adjacent punctures, and I want to think of the subgroup of the mapping class group, which is supported inside of that curve, that's exactly the set of braids which use strings 2, 3, and 4, and no other strings. That's exactly the subgroup, which is generated by crossing 2 over 3 and 3 over 4. And that's a standard parabolic subgroup. So the subgroup supported inside of this green curve is a standard parabolic subgroup. The pink curve is similar. So if I wanted to think about the subgroup supported inside of there, well, first I could take the element which moves this leftmost puncture behind the second one. And then that would make my pink curve look like the green one. I could take the standard parabolic subgroup that was supported inside of the green thing, and then I move it back. And that gives me the subgroup supported inside of this pink curve. And so that's just a conjugate of the standard parabolic subgroup. Okay, so key points is that there's a bijection between irreducible parabolic subgroups and curves on the disk. Okay, great. So there's some combinatorial way that makes sense for groups of thinking about curves on a disk. Okay, if we would like to define a marking graph, we should know what curves are. That's good. We should know what disjointness is. We should have some sort of combinatorial analog of disjointness between curves. And this is going to get a little bit technical, but I hope it's not too bad. So a finite-type Artin group has a special kind of element. It has a unique particular element called the Garside element. That's denoted delta. And either this element or its square generates the center of the Artin group. So whatever the central power is, I'm going to denote by Z. A parabolic subgroup of a finite-type Artin group is also a finite-type Artin group, and it has its own infinite cyclic center. And so I'm going to denote that Z sub P for a parabolic subgroup P. Okay, and so it turns out that in the Braid group, 2 parabolic subgroups map to disjoint curves under that bijection exactly when either one is contained in the other, or they intersect trivially and commute. And it turns out that these conditions are equivalent to their centers commuting. And so I've kind of got a picture on the next slide. What this is essentially saying is that the centers of these parabolic subgroups sort of behave like Dane twists around the corresponding curves. So these have the same commuting properties as Dane twists. And so we can kind of think of those as Dane twists. And we can say that the sort of combinatorial analog of 2 curves being disjoint should be when the centers of the corresponding parabolic subgroups commute with each other. Okay, so using that generalization, Completo, Gebhardt, Gonzalez, Meneses, and Wiest in, I believe, 2019, defined something called the complex of irreducible parabolic subgroups. And the idea of this complex was to generalize the curve complex for mapping class groups to all finite-type Artin groups. So vertices in this complex are irreducible parabolic subgroups. So these are in bijection with curves for the Braid group. And there's a vertex between 2 parabolic subgroups when their centers commute. So again, that's sort of our analog of disjointness. And then as before, we fill in any simplices where we see pairwise connected vertices. Okay, this complex is infinite diameter. It's conjectured to be hyperbolic, but most importantly for us today, we know it's finite dimensional. So we know that maximal simplices contain finitely many irreducible parabolic subgroups. And so that leads us to a sort of natural question. Is an element of a finite-type Artin group mod its center uniquely determined by where it sends a finite collection of irreducible parabolic subgroups in the same way that an element of the mapping class group is uniquely determined by where it sends a finite collection of curves? Okay, so having posed the question, I will stop and ask if anyone had any questions about the complex of parabolic subgroups or anything. Okay, great. So in the mapping class group setting, to build a marking, we needed to say, okay, we know what a maximal simplex in the curve complex looks like. We need to think about what its stabilizer is, and then we need to think of what elements we could add in to keep track of that stabilizer. So the first thing we need to do here is we need to figure out what maximal simplices of this complex look like. So we know they're finite dimensional, but we should really figure out what they are. Next step is we need to figure out what their stabilizers are. And then step number 3 is we need to come up with some collection of parabolic subgroups that will allow us to keep track of those stabilizers. So that's kind of where we're going with this talk. So first step, understanding maximal simplices. So if some collection of parabolic subgroups span a simplex, it turns out that there is a single element which standardizes all of them. So in particular, they all look like G conjugating AXI for some AXI. So we can choose the same representative for all of them simultaneously. Okay, so knowing that, it's sufficient for us to understand what maximal simplices whose vertices are standard parabolic subgroups look like, because every simplex we're saying is conjugate to one where all of the vertices are standard. Okay, and so if we have a maximal simplex whose vertices are standard parabolic subgroups, it turns out that we can figure out essentially what that looks like. And so all of them are obtained like this. So I start with a defining graph for my finite-type Artin group. I remove a vertex. That gives me some connected components. Those connected components are irreducible parabolic subgroups. So here I've removed this vertex that's not highlighted in blue from the defining graph for Dn. That gives me 3 connected components. There's a single generator, and these 4 generators. And I add all of those parabolic subgroups into the simplex. Okay, so those are all going in my simplex. Now I look at anything that contains more than one vertex. So here there's only one, it's this 4 generated thing. And I repeat that process. So I remove a vertex, I look at the connected components. Those connected components are parabolic subgroups. They get added into the simplex. And then I repeat until I'm down to single generators. And so here, a maximal simplex has dimension 1, 2, 3, 4, 5, 6. Okay, and so that process completely characterizes maximal simplices. So every maximal simplex can be obtained by a sequence of removing vertices from the defining graph that looks like that. Okay, great. So that's what maximal simplices are. We can then ask what are their stabilizers. Okay, so this is the theorem. Every element of the stabilizer of a maximal simplex spanned by standard parabolic subgroups. And again, remember, it's sufficient to understand the standard ones because everything is conjugate to one of those. So every element of the stabilizer of such a simplex has the following form. So it looks like a product of the special elements associated to each of those parabolic subgroups, raised to some powers. So I take my first parabolic subgroup, I take its special element, which is almost the generator of the center. That's raised to some power. I take the next one, raised to some power. And I've ordered these in a particular way. So that's not so important. Really, the takeaway here is that this thing almost looks like a product of the generators of the centers of the parabolic subgroups in the simplex. So not quite, but almost. I think almost is good enough for intuition for today. Okay, questions about that? Okay, cool. So now we figured out what a maximal simplex looks like. We figured out what stabilizers of maximal simplices are. We can move on to figuring out what we should add in. There's one subtlety here, so I'll go back to the mapping class group case so we can kind of talk about it. So in the mapping class group, a marking added in some curves. Okay, so the first 2 were saying I had a Pants decomposition. I had some curves that had nice disjointness conditions. This third condition, I needed to have minimal non-zero intersection number. So I needed some notion of small intersection that was not disjointness. The reason I needed that was to control the number of markings that have the same Pants decomposition as their base. So that was kind of the reasoning there. In our background section about parabolic subgroups, we talked about curves, we talked about disjointness, we didn't talk about minimal intersection. So we didn't have an analog for that. And so if we're going to proceed to define a marking graph, we probably need to come up with some analog of minimal non-zero intersection. So the intuition is that that is going to be the property of being simultaneously standardizable. So what that means is that there's a single element that conjugates two parabolic subgroups to standard ones at the same time. So two parabolic subgroups, both conjugated by G, now wind up being standard. Okay, and so what's sort of the idea behind that? In the Braid group, two parabolic subgroups are simultaneously standardizable if there's a single element of the mapping class group that sends them to round curves. And that just means ellipses like you see in the right picture, things that enclose adjacent punctures in the obvious way. And so you can sort of imagine, like if I have some curves on the Braid group, here what I've drawn is the green and purple curves on the left are a Pants decomposition of the disk. And then the blue curve is an acceptable tracker curve for the green one, right? So it intersects the green one minimally, and it doesn't intersect the purple curves. And you can sort of imagine like untwisting this green one and these purple ones inside of the blue curve without doing anything outside of it. And then I get to the picture on the right. So there's a single element of the mapping class group, which sends the picture on the left to the picture on the right. That is not a proof that simultaneous standardizability and minimal intersection are the same thing, but it's like kind of some intuition for why this is maybe a reasonable substitution. Someone has asked in the chat. What does intersecting minimally mean? One intersection point or two intersection points? That's a good question. So I am only thinking about the punctured disk. So for me, minimal non-zero intersection number is 2. In general, on a surface, you could have curves that intersect once, but on the disk, that never happens. Yeah, so here, because every curve is separating on the disk, it's always 2. Yeah, good question.
But is it like substantial? Like, can somebody say, okay, for me 3 points? Like, is it kind of like a grocer canal, 2 points, 1 point, 3 points? Like, is there some meaning behind the number of intersection points that that you will allow to?
Sure. So the general idea is that if I were to allow whatever number of intersection points between a base curve and the number, like the curves that are allowed to keep track of its Dane twists, I would have lots and lots and lots of markings with the same Pants decomposition as a base, and I want to restrict that. So this is just some condition that allows me to restrict the possible choices. And it turns out that requiring intersection number 2 turns out to be good enough. Yeah, so that's kind of the reasoning. It's just a restriction on the possible choices. Good. Other questions about this intuition or the mapping class group case or anything? Okay, cool. So the idea is that we're going to substitute in this property of being simultaneously standardizable for minimal intersection number or intersection number 2 to allow us to control the number of choices for tracking parabolic subgroups. Okay, so that brings us to our definition. A marking on a finite-type Artin group we define to be a collection of ordered pairs of irreducible parabolic subgroups. So you should be thinking back to the mapping class group case. This is a lot like ordered pairs of curves, which satisfies the following properties. So first, I want my PI to span a maximal simplex in the complex of irreducible parabolic subgroups. So that's the analog of them being a Pants decomposition. Second, I want the center of PI to commute with the center of QJ exactly when I is not equal to J. So that's the same non-intersection condition from the mapping class group case, just translated to our setting. And then lastly, for each J, I want the collection of all of the base parabolics and QJ to be simultaneously standardizable. Okay. There's a natural action of the Artin group mod center on the set of markings. It acts by conjugation. Okay. We are running out of time, so I think I'm going to skip the elementary moves section. But it turns out there are also natural analogs of the elementary moves for mapping class groups. There are twist moves and there are flip moves, and they're sort of very similar spiritually to the mapping class group case. A twist move is replacing some tracking curve by the thing it's meant to keep track of, and a flip move is interchanging the roles in an ordered pair and then doing suitable replacements on all of the other tracking parabolic subgroups. Okay. So you then define some analogs of these moves, which we're going to leave it as a black box what they are precisely, but they are some sense natural analogs. And then you can define the marking graph the same way you did for mapping class groups. So the graph where the vertex set is the set of markings, and there are edges between two markings that are connected by one of these elementary move analogs. And this proposition is just saying that our substitution for minimal intersection was good enough, and we wind up with a locally finite graph. So we've done suitable control on the number of choices with a particular base simplex. Okay, I'm going to skip that. So the main theorem is that the Artin group modulo its center acts geometrically on the associated marking graph, the same way that a mapping class group acts geometrically on its associated marking graph. Yeah, that's it. Thank you.
Yeah, thank you, Kaitlin, for the nice talk. Let's, yeah. Yeah, there is a, I think, clapping section in there. Yeah, okay. So, so I think we are almost, yeah, if there is any other questions, last minute, please ask.
Can I ask, what is the valency of this graph? How does it compare with Cayley graph?
How does it compare with the Cayley graph? So I mean, it's quasi-isometric to the group, but yeah. How would you like it to compare?
Is it resembling Cayley graph or completely different? What is it?
It's essentially completely different. Yeah. So this is really what this is doing is it's taking some complex that looks like an analog of the curve complex, and it's blowing it up to obtain something that's geometric to the group. But the fact that the action is geometric is not at all obvious in the way that it would be for the Cayley graph.
Mm-hmm. Okay, thank you.
Yeah.
Any other
Are
questions?
these like are these markings like maximal simplicity in another suitable graph? Like in
Yeah,
the
they
spirit of then using it for
Yeah.
hierarchical machinery, right?
Yeah, they should be. So this is going to get a little bit technical. So if you're not used to working with mapping class groups and this doesn't make sense, that's fine. To answer the question, what I've defined are clean markings on a surface. And so the elementary moves are between clean markings, which is some subset of markings. Markings are defined instead of with like curves, they're defined with elements of the annular curve graph about the base. And so you should be able to do something similar, but these are going to be a subset of the markings that will actually give you maximal simplices in a simplicial
Yes. Yeah.
But yes, the answer should be yes. I'm working on that now.
Yes, thanks.
Yeah.
Okay, any other questions?
Do you think it's hyperbolic?
Do I think it's hyperbolic? Probably.
So it's conjecture, yeah.
Yeah, I think generally most people believe that it's hyperbolic. So one interesting application of this marking graph is that sort of the reason that, well, one reason that we don't know it's hyperbolic is we don't really know what geodesics should look like. So there's sort of not a nice picture of what the geometry of this thing would look like. And if you have markings, then you have some hope of constructing an analog of tight geodesics, which you could guess are the geodesics in this complex. And then maybe that gives you some intuition for what the geodesics look like. So I think it's true. And yeah, but I don't know.
Cool, thanks.
Let's thank Kaitlin again for the nice